To get it to dissolve, the flavors to dissolve is to do it when it's a liquid. So you got to do it in a liquid state. So my wife saw this article about nitrogen in a scientific magazine, and I was like, and it did have to do with ice cream, but it didn't say enough of how to do it. So I started contacting like my colleagues and things that people I went to high school or college with in chemistry, because I graduated in chemistry, never seen it done. They said, have you ever seen this done? They said, yeah, but it's not very good. It's kind of crusty on the side, and it's not very consistent. It's really liquidy in the center. They said, we wouldn't recommend it. And I said, can you sell it? And they said, not the way it comes out in the chemistry class. So so I figured it's just a matter of solving the problem. So we went and started testing. What we figured out, and we'll talk more about this, about the phases. This is why observation, this is what about science is about observation, okay? What we observed is, so in this article it said fold like egg whites. Now if you fold like egg whites, okay, it usually means you're trying to incorporate something into a dough. So you're trying to fold and get it to go in softly. Well, nitrogen doesn't dissolve into liquids. Doesn't dissolve into anything. All it does is just evaporate. So it doesn't have a dissolve rate. So I knew that, so therefore fold like egg whites doesn't make sense. I'm thinking fold like egg whites, if that's really what he's doing, then he's using a deep bowl and he's folding, trying to go like this. Tried that, didn't work. So then later, after I had this all developed, I actually went to that author and I went and presented what we found. And he says, never thought of that. Wasn't even what I was thinking. He says, I said, why do you use the word fold like egg whites? He says, I was just trying to make people think I knew something about cooking, so I used a cooking term. He says, it was a joke. Now, the guy's really, really smart, and he's very, very dry. So the sense of humor didn't quite come across as humorous, to most people. But anyway, they thought he really meant what he said. What we figured out is that if we take the densities, you know what densities are, right? Things are less dense float, right? We figured out, and this is known, that nitrogen floats on top of cream or on top of water. So if we take some, not that one, if we take some nitrogen and put it on that water, it floats. Okay, so we know it floats. Floats on top of cream. Okay, what they would do, what the literature before us said, is that if you take a bowl of nitrogen, you take a half a gallon of ice cream mix, you put it in a bowl, and you add about that much nitrogen, 4 ounces of nitrogen at a time, and you stir, okay? The problem with that is if I have this much cream in there, and I pour the nitrogen, nitrogen's really, really hyperactive. And so if I pour it on there, okay, it's just going to make a puddle. It's not going to completely cover. So if I stir, it's really, really hyperactive, and it's going to go right to the edge. If it goes to the edge, then it's going to stick. And it's going to be liquid in the center and really hard on the side. You do it again and again and again, and it continues just to make that just crusty on the outside and liquidy in the center. So what we figured out is if you do all of the nitrogen in at once, that those two phase layers, so it covers the entire surface area, and it creates like a sheet at the barrier, right there where those two layers meet. It creates like a frozen sheet, just like the frozen lake. Okay, and then if we take our spade, it's kind of got like a blade on it, and we go around the outside and break that, and it raises up because it's now, it wants to float because it's a solid. So solid water wants to float, right? So it'll go up, okay, and you have a plowing action. It lifts up, the nitrogen goes to the next layer and does the same thing. So it's like a slicer, like a meat slicer, and just slicing a piece of meat, but it's doing it with a solid liquid phase where you're creating the phase and separating it from the rest of the liquid. until there's nothing left frozen. We got a patent on that, so that's really unique. But densities, understanding or really observing those densities and how those interact matter. And so now let's talk about nitrogen. So first of all, is water a liquid? Yeah. Water's a liquid. Okay? Water's a liquid. So it's is it always a liquid? No. So most things, all things, I would say most all things have different states: solid, liquid, gas. There are some exceptions. For the most part, huh?
This has two, right? It's like
You could make molten, and you could probably get it to vaporize. I don't know. I don't know what the vapor. I haven't really looked like aluminum. Aluminum probably does have vapor where it would burn, or at least it would oxidize. I don't know. I'm not sure if it's got a gas phase, but it'd be really, really hot. So but yeah, I mean, most things have at least two. You know, like liquid or gas or plastics might burn, but they typically have a liquid phase too. So but anyway, the point of the matter is that there are three phases, okay, with water. Now you can get more specific, like ice actually has 7 different phases within ice, but we're not going to go into that right now. So the point of the matter is, why do we call it a liquid when it can be a gas and when it can be a solid? What makes it a...
because it's in the fixed state as
Right. But if I'm not looking at this and I just say water, how do I know what state it is?
because like most people think of water as a liquid, and like you would say boiled water, and that would be like vaporized.
You're very close. There's a standard. Well, no, okay. I'm not saying that it isn't water. What I'm saying is that we call it a liquid because at standard temperature pressure, so there's a scientific term, standard temperature pressure, it is a liquid. So we call nitrogen a gas, okay? It's a gas at standard temperature pressure. 78% of the atmosphere we breathe, 78% of the atmosphere we breathe, 21% of the atmosphere we breathe is oxygen, but 78% is nitrogen. But it's a gas at standard temperature pressure. Now, at standard temperature pressure, let's define that, is at room temperature and sea level. So 1 atmosphere. 1 atmosphere is measured at sea level. I believe it's like 15 pounds per square inch, or it's 1 ATM. So atmosphere, 1 atmosphere. So anyway, but we are at less than 1 atmosphere here because we're at higher altitude, right? So, so if we have, so at standard temperature pressure, if I say water, I'm assuming a liquid state. If I say frozen water, then it's a solid state. If I say gaseous water, now I'm specifying a different condition. So it's not the fact that I'm specifying something else, I'm specifying the condition. So if I say liquid nitrogen, I'm specifying the condition of that nitrogen. And that nitrogen is liquid. Okay, so that means that in order for it to be liquid, it needs to be negative 321 degrees below zero, or 195 Celsius. Okay, so if I say liquid nitrogen, then that's specifying not standard temperature pressure, a new condition, negative 300, it must be below that. Okay? So if I say solid water, what's the new condition? No, I mean temperature-wise.
25 degrees.
25?
Below 30 degrees.
32. 32 degrees Fahrenheit or 0 Celsius, right? So, okay, so we're going to take this valve off. This I better turn it off. Okay, take it off. And there's liquid inside here. Okay, it's gonna come out. There's also water vapor in the air. So it's gonna come out cold. And as it comes out cold, okay, it's going to vaporize or condense the water vapor in the air and make a fog. Okay, as it